So this is our second lecture on refrigeration and heat pump systems or cycles. Last time we talked about the Carnot refrigeration and even alluded to what is wrong with it. And so I'll summarize there to bring us to the vapor compression refrigeration cycle. I think this is one of the shortcomings of maybe engineering thermodynamics is we have the Brayton cycle, we have the Rankine cycle, we have the Otto cycle, we have the diesel cycle, but we have no name for the vapor compression refrigeration cycle. I think it should be the Carrier cycle, or somebody should be honored with their name attached to it, but hey, I don't carry that much weight to be able to do that, but somebody should be honored. So let's press forward. So everything on this side is review. It's the Carnot. What do we have? 4 components. You have a compressor, you have a condenser, you have a turbine, and you have an evaporator. Now, the heat transfer is into the evaporator. It's picking up because it's at low temperature. In theory, the fluid in the evaporator, the working fluid, is at TL, and that's the same temperature as the reservoir at which there's heat being transferred out of. So both of these are the same. You then come in with a 2-phase mixture. It's high quality, but it's not saturated vapor. You put it through a compressor and you come out with perfect saturated vapor. That's hard to do, very hard to do. But this is in theory, like a frictionless pulley is pretty hard to do, but this is similar. Then you go in the condenser. The working fluid all the way through the condenser is always at TH, which is the same as the high temperature reservoir at which you're dumping heat to. So you have 0 delta T up here, 0 delta T up here. You're saying, how are you going to ever transfer heat? Well, be very patient and wait a lifetime, or have an infinite heat exchanger. But you know that's in the limit to have no delta T, and yet you're driving the heat transfer. Again, it's like a frictionless pulley. But that's our assumption, that the working fluid's all at TH while it's rejecting heat to a reservoir at TH. Then it comes out saturated liquid. And so on a TS diagram, when you put the dome in, it pins the upper corners on that TS diagram at state 2 and state 3 is saturated liquid, saturated vapor, saturated liquid. And then it goes state 4 and state 1 on a temperature entropy diagram. All right, we covered that last time. So what's different? Well, for the actual vapor compression refrigeration system, which is the majority of the refrigeration systems out there, in your automobile, in your home, in your refrigerator, freezer, there's a lot of vapor compression. What we do is we still have a compressor, but we don't ingest a 2-phase mixture of high quality liquid vapor. We ingest saturated vapor. So it comes out of the evaporator completely evaporated, which means when I put it through the compressor, even if it's isentropic, so state 1 shifts all the way over to here. So even if I have it isentropic to get up to that line of high pressure, guess what state 2 is? Superheated. And that's a key concept. It's now superheated at state 2, which means for the first section of this heat exchanger, it's going to de-superheat the refrigerant, meaning that it's going to cool it. It's going to be rejecting heat, but as it rejects heat, it'll finally get to the point, maybe it's at this point, where it's now saturated vapor. And as I continue to cool and move along, it now condenses. Now, right away, it's the majority of the heat then is transferred out of the refrigerant while it's at TH, but some of the heat's transferred out where the T2 is greater than TH. It's got to cool it down. So you can see that here. You got to cool it down before you can start to condense. So state 1 is pushed over, 2 is over here on a TS diagram. We still come out of the condenser fully condensed. That's saturated liquid. Then we put it through not a turbine, but we put it through an expansion valve, which has some irreversibility. So it has some higher entropy S4 coming out is going to be greater than S3 going in. The second law analysis. So when we come over for 3, we dash line over to state 4, and 4 has a higher S than 3, than it used to have. S4 is higher than S3. So there you go, that's it. So what are the 3 big differences? The big difference between the Carnot and the actual vapor compression refrigeration is we don't have a turbine, we just have an expansion valve, which is irreversible. We have inlet to the compressor is saturated vapor. It's been shifted from here to here, see, saturated vapor. And when you then put it through, you get superheated vapor, hence not all of the heat rejection is occurring at TH. Some of it is associated with cooling it from T2 down. Think of sources of irreversibility. One of them is heat transfer through a finite temperature difference. So it's going to be more irreversible in that condenser because it's having to reject. You can't, let's say this is at TH right here, the saturation temperature, Tsat at the condenser pressure. Well, you're going to have where you dump it to, that has to be lower than T2. The maximum it can be is T2. Right.
Where is work coming out of that system?
Work is only going into it, and it's no work coming out. It's just you supply work to the refrigeration cycle. All right. So that's the big contrast. Is this, I'll repeat, is this the way your automobile air conditioning system works? Yes, it is. Is this the way your home air conditioning system works? The window unit, the central system, yes. Is it the way your refrigerator works? Yes. And probably a number of other systems that are refrigeration based. All right. So set up and solve a problem. So you read the problem carefully and organize the information. It's very similar to the problem that we solved last time, but it's not a Carnot refrigeration cycle. It's a vapor compression refrigeration cycle. The same working fluid. The pressure of the evaporator is the same, meaning most of the phase change is happening at 4 degrees C in the evaporator. And most of the, well actually all of it, because the evaporator is going to stay isothermal, but the condenser has the same pressure and most of it is going to be condensing at 52. It's going to come down into the condenser initially more like 56 degrees C. It'll have to cool to 52 before it starts to condense in the vapor compression refrigeration. Our standard assumption about saturated vapor exits the evaporator, saturated liquid exits the condenser, give the same mass flow rate, and determine the same things that we did for the Carnot cycle. What is that rate of heat transfer to the refrigerant in the evaporator? 10.4 kilowatts. What is the net power into the cycle? And then what's the coefficient of performance? And that'll be lower or higher or equal to the coefficient of performance for the exact same condition, same working fluid when it was Carnot. Can you tell me which way it'll be? The COP for refrigeration cycle, the Carnot, compared to the COP refrigeration cycle, I'm going to say VC for vapor compression. Okay? Will it be, the Carnot will have a greater or an equal or a lower coefficient of performance? I'd like you to answer that question. I'll pause, walk around, and see what you come up with. This is the COP. Higher the COP, the better. If it's more reversible, you're going to have a higher COP. And it's limited by the temperatures. What did we get for the COP of the Carnot refrigeration? Was it TL divided by TH minus TL? Yeah, something like that. You can get it higher if the smaller delta T's between the high and the low. You can get a higher COP, but it's maximum COP is given by the Carnot. So anything is going to have a lower COP for the same two temperatures. So, okay, so what is the strategy for now solving for part A, B, C? Step 1, give me a schematic, names of the components and locations of the states. True? So that would be like compressor, and then you have the condenser, an expansion valve, and an evaporator, right? And I'd label state 1, state 2, state 3, state 4. And I'd even put down like, oh, it's saturated vapor here and saturated liquid there. So some sort of schematic. True? What's next after the schematic? Make a property diagram, and one of the favorite is temperature entropy diagram. We're also going to get the pH diagram in a minute. Another property diagram, a pressure enthalpy diagram, which is very useful for these types of systems. But we're very familiar with the temperature entropy diagram. Let's go ahead and show it here. What about the PV? Not really, not for this system. Okay? All right. Once I have my schematic and states labeled and description of the states for some of them, and I have my temperature entropy property diagram, what next? Make a table and calculate all the properties at each of the states. And you think about, what are the properties? Well, make the list. This is a generic list. If you just could rattle this list off every now and then, it would help you organize the solution strategy. Pressure, temperature at the top of the list. Then you go specific volume, internal energy, enthalpy, entropy, flow exergy, and probably a few more. But for this type of problem, experience will show that really, if I need to size the tubes, I need to know maybe the mass flow rate, and I need to know the specific volume, then I get how large of a tube I need. And believe me, that's a real consideration for engineers. But in this class, for this chapter, that's more of fluid mechanics. We're not really going to use V. How about U? Well, each of the components is solved by a control volume around the turbine, around the compressor, around the, not the turbine, expansion valve. So you don't really need, which one do you need a lot? H. And then you're going to use the S quite a bit. And the flow exergy, yes, you can use that. But believe me, if I can just get students to solve problems with, enthalpy and entropy, I'm sure they can do the flow exergy, exergetic analysis of the system as well. So make a table of the properties. After you get a table of the properties, make a table of the Q's and the W's. I call those the transfers, the transfer of energy for each of the components. Is it transfer of heat in or out of that component, the work in or out of that component? And then check energy balance, and then just solve for the unknowns. Now, I know that you would like me to go maybe slowly through each step of this. Maybe, maybe not. But I think we're at the point where this kind of makes sense. This is our schematic. This is all of our components. This is a description of key states and numbering of the states. We could put our diagram together. I've done it a couple times. TS, put the dome, put now state 1 there. 2 is going to be superheated. Constant pressure from 2 over to saturated liquid. 3, dashed line down to 4. Why do we put a dashed line, not a solid line between 3 and 4? Because the area under that line does not mean anything about the heat transfer. Where if it would have been a reversible path, yeah, but it's irreversible. Nothing to do with the area under the curve. So that's the convention to use dashed lines when it's irreversible. All right. We then put little notes like, oh, it's state 1, it's saturated vapor. And either you know the temperature or the pressure. Both of them are given. There's the pressure of the evaporator, there's the temperature of the evaporator. Okay. And then you can just get, what is this H right here? If it's saturated vapor, it's Hg. And then this S, Sg, and the quality is 1. All right. Then we go to state 2. Well, basically it's the pressure and the entropy fixed state 2, P and S. So this S comes down, and now I have the chore of looking up H as a function of pressure and entropy. I know where I'm going to have to look. Don't look in the two-phase table, right? If you do and you calculate it, you'll find a quality of about 1.04. What does that tell you? It's outside of the, the quality can't be greater than 1. It's outside of the two-phase table. Now, you can still use that to get an extrapolation of the enthalpy at state 2, But the proper way is to go to the superheated table, and if you've done this once or twice, it's like a painful memory that you have. Because this looks like I will be needing to do a double interpolation. Does that get you excited? Not at all. But unless you've done a few double interpolations in your life, then you don't know. But it's a big deal to have to do one or two of these in your lifetime. So do it if you haven't done them, or do a few more. But I'll just let you know that if you take and extrapolate and use the quality, which is not recommended, above 1, and you calculate H that way, and then do the double interpolation in the superheated table and compare that H with that 2H, they're going to be pretty close. They're going to be pretty close, right? What's the best way? Double interpolation. The other best way is, come on, computer program has a lot of this implemented, right? What year is this? Is this 1950? No, it's not 1950. It's 2017. It's hard to keep track of the years. So anyway, we keep going. Saturated liquid, knowing the pressure, saturated liquid, same thing. What is this? H? H of F, S of F. We really, after you've solved a few of these problems, you really don't need that S anymore because it's going to be irreversible. But you could get it. And then when you go, it's a pressure and enthalpy. How do I know that H4 is equal to H3? And I hope you can prove that to a skeptic. Maybe you have a study person, mate, or something like that, and they're like, I don't believe that. I hope you can prove it to them. How would you go about proving it to a skeptic? Do an energy balance. No Q, no W, or Q dot and W dot. No change in kinetic and no change in potential. You're left with the realization, steady state, H is, it's isenthalpic. I get into people question me about that all the time.
Can we have an isotopic efficiency?
For a turbine? I mean, an expansion valve?
Yeah.
I've never seen one defined. What in reality, though, is you will have a little Q dot either into or out of that device because they, if it's cold, the surrounding room is a little warm, there will be a little heat transfer. But basically, it's so small and so small of area that it's a very small amount of heat transfer, and you neglect that heat transfer. Right. Once we have our table of properties and what column is the most important, the enthalpy column. Then you go to our table of transfers, heat and work transfers, and we standard assumption about the compressor. Now, if anybody's been around a real air conditioning compressor, it's been running for a long time, and you just reach up to your hand and touch it on the side, guess what? It's hot. The compressor is really, really hot. Now, in practice, do the engineers wrap an insulating blanket around the compressor? No, because if there is a little heat transfer, it's only going to help. So if there's a little bit of heat transfer to the outside air. Now, they don't put the compressor inside your house. Think about that for an air conditioning system. Where do they put the air conditioning compressor? On the neighbor's bedroom side. That's where that goes. Not your bedroom side, out toward your neighbor. No, I'm just joking. It's loud. You ever heard when they kick in, the fan and the compressor running? Anyway, they're not insulated. If there's a little heat transfer, it only helps the system. But the standard assumption is 0. Same with the condenser. There's no work, absolutely no work. But there's no pressure drop in our analysis either. Real condenser will have a pressure drop. Likewise for the turbine. Now, I put minus signs because it's not heat transfer into the condenser, but out of the condenser. So when I do the sum of the Q's, the net Q is out of the system toward the hot. And the net work is not out of the system, but into the system.
So on a test on the homework, which you want our answers to be negative or positive, depends how we...
Whatever can prevent you from making an error. And believe me, I can solve it both ways. And I can figure it out both ways. As long as you're consistent with yourself. I like all positives. But then when I try and explain it to people, it seems to be more difficult, so I try to put the negatives in, and every now and then I trip on myself because of that. But yeah, do it the way that is less error prone for you. And then you just calculate those quantities of interest. Notice the COP based on a Carnot was 5.7. It's dropped. It's not going to be as efficient, not going to be as good. The coefficient of performance is lower. And I think the refrigeration tonnage is about the same, but you require more work. More work. Can you solve a problem like that? What do you think would be a change to that problem? Yeah, somebody says, oh, change the isentropic efficiency of the compressor. Redo. But the big change is only going to be if I put it on a temperature entropy diagram, put on my low pressure line. Is that the evaporator pressure that's low or the condenser pressure that's low? The evaporator pressure is low. Then put on the higher condenser pressure. I'm still coming out saturated vapor state 1. I put it through the compressor. If it was a perfect compressor, it would be 2S. But where is 2 actual now? It's even going to be worse. A higher temperature to the right, because you have to increase in entropy because of entropy production irreversibilities. So maybe you're out there and you can solve that problem. It's just 2 steps to go from state 1 to state 2. That's 2S, and then it's 2 actual. Let me rewrite 2S. All right. Here are the numbers. Guess what happens? The COP even goes down lower. You would expect that. More friction, more irreversibilities, more losses. And you're going to slip a little bit in the tonnage, not much, but the power goes up. All right. The 2 diagrams that you really want to be comfortable with, and I've sketched the temperature entropy a couple times. For water, it's very symmetric. For refrigerant 134A, it was a little steeper over here. Let me try and draw it again. Like that. It's a little steeper on the right. Okay? To temperature entropy diagram. And then what is the point at the top up here? The critical point. All right. The other property diagram is new to you. You haven't seen it, but it's very helpful. It's the pressure enthalpy diagram. The dome on a pressure enthalpy diagram looks like this if you plot the log of P. So it's going to be a semi-log plot, not a linear plot. Did you have a question? This for refrigerants, typically they're steeper over here. And for water, it's more symmetric. Okay. But so maybe this is like 10, and then 100, then 1,000, and kilopascal or something like that. So it's on a log scale for the pressure. Otherwise, if you plot linear, it won't look that way. And right up here is the critical point. And what is the sequence of all of these states? It's still the dome, so all those states are saturated vapor. Saturated vapor, aren't they? Saturated vapor. And what are all of these states? Saturated liquid states. Saturated liquid states. So let's go ahead and think of our 4 components. We have the compressor. We have the condenser. We have our expansion valve and our evaporator. And we come out of the evaporator state 1, it's saturated vapor, true? At low pressure. Well, guess what? It's easy to draw a line of low pressure on a pressure enthalpy diagram. What does it look like? Horizontal line, straight. That's right. So let's go ahead and say that this is my evaporator pressure, and this is my condenser pressure. And all 4 of my states are going to be on those 2 lines. That's why we like the pressure enthalpy diagram. Okay, one of the reasons. And so let's say we're coming out at state 1 right here, saturated vapor. Now, a line of constant S isn't easy to do on a pressure enthalpy diagram. It's going to cut like this. And there will be 2S. It'll have a higher enthalpy. It won't be it'll be superheated. You can see it's to the right at that pressure of the saturated vapor's enthalpy. All right. If you have some irreversibilities, guess what? It'll even be further out. meaning higher enthalpy at state 2. More work had to go into the compressor, which was added to the enthalpy of the fluid that comes out. All right. So, but when you go through the condense, it's going to condense at constant pressure until you get all the way to state 3. And this is really why they have a pH diagram. Now the enthalpy, because we're at state 4 in relation to state 3. Straight down, straight below. And we would still draw a dashed line indicating it's irreversible by convention. So there you go. Did I tell you a student one time graduated and was interviewing for a job, and he then came to my office. I knew he was interviewing, finishing. He had passed Thermo 1, Thermo 2, and all that. And he said, I have some questions. And he laid them all out, and I started asking me, and I said, are you interviewing for a job? Yes, I am. And they asked me these questions in my interview, and I need to have the answers by tomorrow. Time out. I said, I'm not applying for the job. You are. If you were in my class, I'd answer all your questions. But right now, you're on your own. And they were exactly on the pH diagram. It was just that. It was just the answer. It's rare that in the interview they really get technical with you. They just assume that you passed the class, you learned it once, maybe you forgot it, but you can quickly relearn it on the job if you need to. That's usually the way that goes. They just want to know if you're going to have personal conflicts if they hire you, if you're a jerk. It's true, because if they hire you, most of the time you got to get rid of you because you can't get along with people. Anyway, sorry about the digression. So we have a pressure enthalpy diagram. It's really useful in air conditioning, and so you'll see a lot of that. Now, this is the actual temperature entropy diagram drawn to scale. Notice that state 4 isn't very far off from state 3 on the entropy, but it is for the problem we just solved. And when you go from state 1 straight up to state 2s, it's not much higher temperature if you would have a completely reversible compressor. But if the compressor has the irreversibilities like we just solved, it really does kick that temperature 2 way up. All right? All right. What's it look like? On your pH diagram, again, look at the axis on the pressure. That is not a linear axis. So that's a log axis. So this is your evaporator pressure. This is your condenser pressure. If from 1 to 2s, it's slightly superheated, to actual, much more superheated. And then you have saturated liquid at state 3, and then straight down on the enthalpy for state 4. A couple questions for you. The pressure in the evaporator. Now I'll take a volunteer that will raise their hand. I'll get their attention. You're the first one. So the pressure in the evaporator is either high or low. It's low, right? You can't answer any more questions. Next volunteer. All right. The temperature in the evaporator is low. You're correct. The next volunteer. All the way in the back. Yep. Did you raise your hand? You were scratching your nose. Convenient time to scratch your nose. All right. The refrigerant leaves the compressor and flows to the condenser. True? True? You're next, okay? Refrigerant leaves the condenser and flows to the expansion valve. You're right. And who's my next person? Everybody that participated is offline. They can't participate. You scratch your neck. You caught my attention. He's scratching his nose. You're scratching your neck. Go ahead. Isothermal. Flow through the evaporator. All right? So what's happening in the evaporator? It is definitely isothermal, but there's also one other good answer. What is it? Isobaric. This is Greek, right? But it's temperature equal to a constant. Isobaric, also whatever, Greek or something. What is it? Isobaric is pressure is constant. Very good. So both of you are out. Next one. Flow through the expansion valve is isenthalpic. Is it anything else? Is it isentropic? No. Is it isothermal? Hold it. Is there any heat transfer in the expansion valve? No, it's not. But the temperature changes. The pressure changes. The temperature does change. It's not isothermal. Isobaric, no, huge pressure change. Isochoric, what does that mean? Constant volume or constant specific volume, no. And then last one, refrigerant is cold coming out of the all right, you expansion valve. All right, it's cold coming out of the expansion valve. That's one of the two correct answers up here. Who said that one? Evaporator. It's cold coming out of the evaporator. A lot of people will confuse, they'll think condensing. My experience has been I put something hot on the stove, boil it, to get it hot on the stove, boil. And that's evaporation. It should be hot in the evaporator, but it's not. It's cold in the evaporator. And then the condenser, they think, oh, I put it in the freezer or something. Anyway, the condenser's hot. The condenser's hot.
What's a receiver dryer?
A topic that I don't have time to get into, but practical situations have them. Can you have water or other non-refrigerants get into the system? Yes. Do you have a device to handle it? Yes. Yeah. Your filter dryer is there into it. You also have a receiver for different parts so that you don't get, let's leave that one alone. But let's move on to another topic that I got to get to. All right. Why does the refrigerant get cold when it passes through this magical device called an expansion valve? This is where the student may pass Thermo 2, but not comprehend what's going on, and then will stumble on some easy concepts. So what I do to explain this is I bring in a can of air, but it's not air. What's in this can of dust away so that I can blow off my electronic keyboard, or I can open up and blow off the heat sink, or blow off the CPU, get the dust away, is it's labeled on the can. It's refrigerant 134A. You can buy it at Alltech just around the corner from us or other places. Now this can, if I take the fluid in it and I go like this, and if you don't know what I'm doing up here, please pick up this can at the end of class, shake it a little bit. What do you think I'm able to experience? Sloshing. There's sloshing. What does that indicate about the substance, the condition of the fluid in this can? There's some liquid and there's some vapor together. Okay? Now, if I sit it down such that the top, is up, straight up, where did my pen go? And gravity is this way, right? Gravity is this way. Which collects at the top? The vapor. When I push on this little handle right here, what goes through the little expansion valve and then squirts out? Vapor. And so when I do it like this, but you probably wanted to explore the world when you were younger. And you took the can and you turned it upside down. And then you pulled on the trigger and there would be, what are you seeing now? Compare. And compare. You're seeing liquid refrigerant, or also you're seeing also the possibility of condensation in the humidity in the room when exposed to something really, really cold. Okay? Kind of like when you blow your breath in the winter. But anyway, right here, if I turn it upside down, what's next to the valve when I press it? Liquid. Liquid's going to go through the enter in the expansion valve. When I do this, I can blow it on my skin. I can feel it's not cold. Do not turn it upside down and blow it anywhere near you, on your skin or anywhere else, because it will lead to a burn known as it'll be a freeze burn. So I have a clean, believe me, I didn't use it, handkerchief that I can carefully close this in and turn it upside down and squirt a little into it. Then I'm going to throw you the handkerchief and you're going to tell me how hot or cold that handkerchief is going to be. Right now, the handkerchief came out of my pocket. It's room temperature, if not a little warmer. When I throw it to you, after I spray this refrigerant into it, what do you think it's going to be? Pass it to your friend. Pass it to a few until it heats up. It's almost unbelievable, isn't it? How cold that is. Is that really, really that cold? You're something. No, you put a thermocouple on it, it's cold. And so what is happening? Why does the refrigerant? There must be a lot of heat transfer out of the system in this expansion valve. Does that explain the lower temperature? No, the Q dot's 0. Well, it goes back to the intermolecular forces. When you put a pot of water on the stove, you put heat into it, that led to boiling. You had to pump energy into the system in the form of heat to break intermolecular forces, or those bonds between the molecules. Same thing with refrigerants. When it's in a liquid state, there's things holding it together in the liquid state. You have to pay a penalty. You have to put some energy in to break that intermolecular bonds or forces. And that is why you have it. So if you think about your old friend, the pressure temperature diagram, you go from the triple point up to the critical point, and we're thinking of you're being a saturated two-phase liquid vapor mixture, right? You immediately drop the pressure. Where does it want to go? It doesn't want to go from liquid. It wants to go into the vapor state. But you can't break those molecular bonds without supplying some energy. But it's like you take out of one pocket into the other pocket to get it back over to the two-phase region. But that two-phase region will be at a lower pressure, but it'll also be at a lower temperature. So when we put it through the expansion valve, you can think about roughly 1/3 of it, quote unquote, flashes. What do you mean by flashes? It promptly goes into the vapor state. It took some energy to make it go into the vapor state. Basically, 2/3, all of it's at the lower temperature, but 2/3 had a significant reduction in the temperature of that liquid. So there you go. That's the best I can do. You have to think about it. You have all the tools to explain it. All right. How many people have seen HVAC technicians? They come out with gauges, hook it up to the system. They are reading the high pressure side, low pressure side. It's like your blood pressure, and a medical doctor, they could tell a lot about your system. Oh, this is the sickness of the, what's wrong with you, and that's how I'm going to fix it. Anyway, there's a lot of these. And this gauge, I have another gauge blow up on it. And this gauge over here really is telling you the pressure temperature data, like on that chart. They'll even call it a pressure temperature chart. The old refrigerant guys would have a little card in their pocket, and they'd pull it out, and they could look and say, okay, what refrigerant am I using today? Oh, it's 134A. And they'd say, what is the pressure, or what is the temperature right here? Maybe they come down here, and they say, at -8, I expect the saturation pressure to be 117 kilopascal. This is the pressures in kilopascal, and the temperatures in degrees C. Somebody says, what is the pressure of the refrigerant in this can right now? Could you even come close to a guess of the pressure of the refrigerant in this can? It's a pure 134A. You have all the tools to tell you that, right? And you take this can, and they say, don't set it in direct sunlight. Why? It'll get a lot hotter, and the pressure, will it stay the same, or will the pressure go up? It'll go up. Don't take a can like this and throw it into a fire. They say don't put it in sunlight and don't throw it into a fire. But I know some of you have been naughty, and you've taken spray cans and other things and throw them in the fire, and then you get away, and then all of a sudden there's some pop, explosion. And this will really blow. This will blow. So anyway, what is the temperature in this room right now? Can somebody tell me? In degrees C, close, what is the temperature? Let's pick 24 because there's a number. This was refrigerant 134A. That column was blue for that refrigerant. The pressure is 550 kPa. That's the pressure in here. Let's say I bump it up to 40 degrees C. Well, it just went up to 900. I hope the can take it. Well, it can take it. But I don't know what the limit is on this can. But I'm sure somebody on the internet says don't tilt the can and use it either when you spray on the label. There's a lot of nasty. I did some wrong things with it. Anyway, careful. if you get one of these gauges, they basically give you the PT diagram in the face of the gauge. The outer is the pressure in PSI starting at 0, 20, 40, going around. But if you know the pressure and you know what refrigerant you're measuring, oh, you're measuring 410A. If you're out at 60, then the temperature is in degrees, where is it listed? Is it degrees? Oh, degrees F right there, yeah. Then its temperature is 10. That's the saturation temperature. So the PT chart, which you thought was confined only to thermo books, no, it's in the technician's pockets. It's on the technician's gauges for the refrigerant 12, 134A, 22. Different refrigerant gauges, have different labels on them. Anyway, also, we've moved into the digital age. Now the technicians hardly even have to read a dial gauge. They just hook it up and it's digital readout. And not only that, they hook up this device which measures the temperature, physical temperature on that line. And then they hook up the gauges to measure, and they get the high pressure side, the low pressure side, and they can do a full diagnostic on your system. So think about your pressure gauges. I have a favor as I wrap this up. Let me stop right now.